Okay, let's start. So today I'm going to talk about characteristic polynomials, minimal polynomials, and the Jordan block or Jordan form of a matrix. Professor Vero asked me to talk about this, so you kind of can think about this as part of the material that you're supposed to know. Okay, so let's start. We start with the matrix A, right? Suppose A is a matrix. And remember, to A, we can assign a kind of matrix polynomial, which is determinant of A minus lambda I. And setting that equal to 0 gives us an equation, right? This polynomial is called the characteristic polynomial. And remember, the roots of this polynomial, different values of lambda satisfying this, are called eigenvalues. Now, there is an interesting thing. There's an interesting theorem called Kaylee-Hamilton theorem. I mentioned that the other day. Today we are going to kind of build up towards that. So this is one thing we have. So the second concept. The second concept I want to define is called minimal polynomial. So in order to define this, suppose we have any given polynomial, real valued polynomial, for example, or over any other field. For example, suppose px equals to an x to the n plus an minus 1 x to the n minus 1 plus a1x plus a naught is given, right? This is just a polynomial. For example, well, just as an example, let's write something. X cubed minus 2x squared plus 3, something like this. We can change the form of this polynomial into a kind of something. In this course, we would call it a matrix polynomial. So here, when I write this polynomial, in our mind, we think about x as something which can be a real number. We can plug in a real number, right? It can be 0, 1, minus 1, anything like that. But the point is that we can also plug in matrices inside this equation. But in order for that to make sense, we should change something here slightly. So I would show it again with P, say A, for a matrix A, any matrix A. Any square matrix. So I'm assuming it's a square matrix. For any matrix, we can define the same thing. We can look at A cubed, just a matrix multiplied by itself 3 times minus 2a squared. And then always, rather than having that constant number plus 3, we add plus 3i. This is the identity matrix multiplied by number 3. So this is just 3, 3, etc. on diagonal. So we can rewrite a matrix for a matrix, right? We can rewrite a polynomial for a matrix. We can plug in matrices into polynomials. Now, what is the minimal polynomial? By a minimal polynomial of a matrix A, for a given matrix A, suppose a matrix A is given. For a matrix A, the minimal polynomial is a polynomial which, if we write it in matrix form, the matrix A would be a root of that. So it's a polynomial like Px, some polynomial, say an x to the n plus up to ax plus a naught, such that it has 3 properties. One, P of A, if we plug in the matrix A inside this polynomial, we would get 0. That's 1. 2, it is monic. What does that mean? It means the coefficient of the term with the highest degree is 1. So it's just an is just 1. That's the second property. The third property, which refers to this word minimal here, that's the reason why we call it minimal, is that if I find any other polynomial like qx, any other polynomial, the degree of p such that a is also, if I plug in a into that polynomial, I would still get 0. The degree of p is less or equal than degree of q. Okay? Degree of p is less or equal than the degree of q. Okay, does this definition make sense? So for any matrix, I would define minimal polynomial to be just a normal polynomial like for ordinary real numbers or any field, such that I can, if I plug in the matrix into that, I would get 0. And it is minimal in the sense that its degree is less than degree of any other polynomial, which this matrix, given matrix, is also root of that. Also, the coefficient of x to the n, top degree, is equal to 1. This is called minimal polynomial. And then the theorem is that for any matrix, this minimal polynomial does exist. We have this minimal polynomial and it is unique. So theorem is that for any matrix, we have existence and uniqueness. Okay. So yeah, there is a question in the comment. This is exactly the direction we are going towards. I would address that question. So now there is a theorem known as Kaylee-Hamilton theorem. Kaylee-Hamilton. So it says for any matrix A, we can look at this polynomial, determinant of A minus lambda I equals 0. And we would get a polynomial. So if I just change the notation slightly, so it is compatible with the notation we had in the previous slide. If I just write it as determinant of A minus xi, this would be a polynomial in terms of a variable x, right? So for example, if A is this matrix, 2, 3, 1, 0. If I look at A minus xi, it would be this matrix 2, 3, 1, 0 minus x times I, which is x, 0, 0, x, which is equal to 2 minus x, 3, 1 minus 0, 0 minus x, just negative x. I can look at determinant of that. So if we look at now determinant of A minus xi in this example, we would have x times x minus 2 minus 3, which is x squared minus 2x minus 3. This is the characteristic polynomial of this matrix. Kaylee-Hamilton theorem says the matrix A always is a root for this equation, determinant of A minus xi equal to 0. A is always a solution for that. It means if I write A squared for this matrix A here we started with, minus 2A minus 3I, if I compute that for this specific matrix A, the result would be 0. This is called the Kaylee-Hamilton theorem. Okay. So For any matrix, we at least have one specific polynomial, which A is the root of that. The characteristic polynomial is that matrix. But this is not necessarily the minimal polynomial. What do I mean by that? There might be a polynomial of lower degree, which this matrix is also a root of that polynomial. Okay? Now here, in this specific question, suppose for this specific matrix, A, I want to see what is the minimal polynomial of A. What is the minimal polynomial of A? So you see here, I have already found the Kaylee-Hamilton theorem tells me the matrix A always satisfies its is a root of its characteristic polynomial. So I've already found one polynomial which A is a root of that, right? If there is a minimal polynomial, the degree of that polynomial should be less than the degree of this polynomial here, right? Here the degree is 2. So if there is a minimal polynomial, the degree of that should be 1, right? So question, is there any polynomial with degree 1, which A is the root of that? Is there any polynomial degree 1? Like, let's show it with m of x, such that m of A is equal to 0. Oops, I can't write here. Okay. Is it yes,
there is.
There is?
I think so, because wouldn't that just be the A minus eigenvalue times I?
Okay, let's see. So here the matrix is 2, 3, 1, 0. I just write that one more time. So any degree 1 polynomial is of the form ax plus b, right? Because it is minimal, we assume the degree, the coefficient of the term with the highest degree, we assume it's always 1. So here a here has to be 1. So it should be of the form x plus b. If I write that in the matrix form, m of A would be A. I would just plug in instead of x. And instead of B, we would write B times the identity matrix. So this would be 2, 3, 1, 0 plus B times the identity matrix, which is B, 0, 0, B. Now this sum is equal to 2 plus B, 3, 1, B. We want this to be 0. Is it equal to 0? The 0 matrix? No, it's not. I mean, well, even for any choice of B, well, I mean, still we have 3 here and we have 1 here, and they can never be 0, right? 3 is not 0, 1 is not 0. Doesn't matter what number you choose for B, this matrix is not going to be 0. Okay, does that make sense?
Yes.
Is there? Yeah.
Yeah.
I just
Okay.
have a question.
Yes.
Can you think of finding the minimal polynomial of a polynomial as writing the polynomial as say x minus root 1 x minus root 1 to the power of k, x minus root 2 to the power of j, and so on for all the roots? Any polynomial can be written like that. Would you get the minimal polynomial by just setting a equals 1 and all of the powers j, k, and so on to 1 as well?
No, you're saying, if I understand correctly, you are proposing this conjecture that minimal polynomial of any matrix should be x minus its eigenvalue first eigenvalue to the power 1 times x minus its last eigenvalue to the power 1? Is that what
Right.
you are guessing?
Yeah, or rather that, right, that's what I'm guessing.
Yeah, that is close to the correct statement, but it's not true. Sometimes these powers, sometimes they are not 1. They have a geometric meaning, which we will talk about that.
Right.
So that's
thank
very
you.
close to being the correct statement. So let's get there. Let's not get ahead of ourselves. Okay. So in this case, it means there is no polynomial of degree 1, which this matrix is a root of that. And therefore, what we have here already is the minimal polynomial. It is the minimal polynomial of A. Okay. Okay, that's, yeah.
Do we know this is unique?
Yeah, this is unique. Yeah, I would also mention why. That's a very good question. Thank you. But before arguing why the minimal polynomial always exists and it is unique, let's look at this equation we got here. X squared, or the same one here, x squared minus 2x minus 3. So we have this polynomial 2, 3, 1, 0. And the equation, the minimal polynomial is x squared minus 2x minus 3. Yeah. Equals 0. Well, the point is that if I look at this matrix A, and if I want to find its eigenvalues, well, specifically here, it's very easy to do that because this minimal polynomial is the same as the characteristic polynomial. But anyway, if we try to find the eigenvalues, I should exactly solve this equation, right? Because this is the same as the characteristic equation, A minus xi equal to 0, determinant of that equal to 0. And we got this equation, x squared minus 2x minus 3 equal to 0. And then x is 2 plus minus 4 plus 12 over 2. So one of the solutions is 2 plus 4 over 2, which is 3. The other one is 2 minus 4 over 2, which is minus 1, right? So this equation can be written as x minus 3 times x plus 1. Now, there is a point here. It is important. The observation here is that the minimal polynomial, which here is equal to characteristic polynomial, can be decomposed into x minus eigenvalue of the matrix. Now, it is trivial because the minimal polynomial in our example is equal to our characteristic polynomial. But actually, that turns out to be true in more general case. What do I mean by that? So we have the characteristic polynomial. Suppose I have the matrix A. I am forming this matrix A minus xi. I compute its determinant. I would set it equal to 0. It is a polynomial, right? And it can be written as, say, p of x equal to 0. Now, suppose there is another polynomial, which is the minimal polynomial of the matrix A. Suppose we have the minimal polynomial of the matrix A, m of x equal to 0. Because of Kaylee-Hamilton theorem, we know p of A is equal to 0. And by definition of the minimal polynomial, the matrix A is a solution to this equation. So m of A is equal to 0. Okay, great. Now, you know we can divide one polynomial by another polynomial. I can divide the polynomial px. I can divide it by polynomial mx. Just like we divide a number by another number. Okay. So suppose here the result is m times some other polynomials. Q of x would be something, and then there would be a remainder. Let's show it r of x. It's just similar to the way we divide integers by each other. So p of x is equal to m of x times q of x plus r of x, which r of x is the remainder. Now, there is a condition the remainder satisfies. Does anyone remember? The remainder of this division should have some property.
I think that its degree is less than or equal to the degree of m.
That is correct. So degree of this r is less or equal than the degree of m. So let's see, what is this r? I mean, if I plug in a into this equation here, what would I get? I would get p of a equals ma qa plus ra, right? But we know ma is 0 and pa is also 0. Therefore, ra has to be 0. Isn't it a contradiction? We found a polynomial which its degree, actually it should be less than m. I wrote less than equal, it should be less. So isn't it a contradiction? Shouldn't we have a polynomial, its degree is less than the degree of the minimal polynomial, and a satisfies that. Isn't it contradiction with the definition of the minimal polynomial? Wasn't it supposed to be the polynomial with the lowest degree, which a is a root of that?
Wouldn't the remainder just have to be like identically 0 then?
Well, yeah, that is true. So the point is that this is a contradiction. It wouldn't be contradiction only if this r of x as a polynomial is just a constant polynomial 0. There is no r of x here. And that's indeed is the case. So if p of x is the characteristic polynomial, and if m of x is the minimal polynomial, there is always another polynomial which you can multiply m of x by that to get p of x. Okay. Now, what does this tell us? So we know the roots of, so any root of px. So suppose we have a number lambda, which is a root of px. What does it mean about lambda? It means it's an eigenvalue, right? It means lambda is an eigenvalue. Okay. Now let's consider the other way around. Let's consider I have a root of m. So suppose I found some number, let's say delta, such that m of delta is 0. So I have a matrix A. I've written I found its characteristic polynomial. I found its minimal polynomial. I've written the minimal polynomial. And suppose I find a real number delta such that m of delta is 0. So p of delta is equal to m of delta times q of delta, but m of delta is 0, so the product would be 0. So p of delta is 0. Therefore, looking at what I've written here, delta is just an eigenvalue. So all the roots of the minimal polynomial, they have to be eigenvalues of the matrix. They can't be anything else. Okay. Now, actually, it's even a little more interesting than that. So if I look at the characteristic polynomial, the characteristic polynomial would be actually x minus lambda 1 to some power times x minus lambda, say, r to some power. So all the eigenvalues, so if one write down the polynomial px, And then let's multiply it by, say, another part. I don't know. Let's call it q of x. Maybe we used q. Say f of x. All the roots of the which this part has no root, no real root. Suppose we are working over R for a second. So we know all the eigenvalues would appear here in this polynomial. So this lambda 1 up to lambda r, they would be, suppose they are the roots of our polynomial. The point is that all of these things would also appear in the minimal polynomial. Let's, for simplicity, suppose we are thinking over C. I would come back to explain this difficulty. Because if the field is C, any polynomial can be we can completely decompose that into the linear factors. So any polynomial can be written like this. Now, the minimal polynomial would exactly have all these roots, okay? All these roots. I'm claiming the converse is also true. Actually, all the eigenvalues, they appear in the minimal polynomial. But the point is that they might appear with a different power. And the point is that Li, the power which appears down here, is always less or equal than Ki. So for example, if we have a matrix, any matrix. Suppose we have written its characteristic polynomial. And suppose it's x minus 1 times x minus 2 squared times x minus 3 cubed. And suppose I have not even seen the matrix A, right? What are the possibilities for the minimal polynomial? The minimal polynomial might be x minus 1 times x minus 2 times x minus 3, because we need to have all factors. All factors do appear in the minimal polynomial. It might be x minus 1 times x minus 2 squared times x minus 3. It might be x minus 1 times x minus 2 times x minus 3 squared. It might be x minus 1, x minus 2 times x minus 3 cubed. And it might be x minus 1 times x minus 2 squared, x minus 3 squared. And finally, it might be exactly the characteristic polynomial itself. Okay? So if I have not seen the matrix A itself, these are the potential polynomials which they can appear as the roots of the polynomial and the minimal polynomial. Okay, let's solve one example, and then we would go a little deeper, and we would understand this thing a little better. Maybe I should just answer one question before I forget that. So the minimal polynomial always does exist. Why? Because we know characteristic polynomial is a polynomial which A is a root of that. Now, the degree of characteristic polynomial is something, let's say n, if the matrix is n by n. Now, there are two possibilities. Either there is some polynomial with degree less than n, like q, which the degree of q is less than the degree of characteristic polynomial, such that this thing also holds, and the degree is non-zero. Or not. If this thing happens, well, then consider q of qx as a polynomial. Now, let's call it q1. Either there is one polynomial with degree less than q1, like q2, such that this thing happens, and degree of q2 is less than degree of q1, and its degree is positive or not. Anyway, at some point it would stop, right? Because degree is a finite number, like the degree is n is like, say, 5, you come down. At some point you would stop. And the last thing you would get is the minimal polynomial. And even if you start from here, and if there is no q with degree less than p satisfying this property, the characteristic polynomial itself would be the minimal polynomial. So this thing always exists. Why is it unique? Well, suppose we have two minimal polynomials, m1x and m2x. So because we as I said, the degree of, so for example, suppose look at m1. m1 is minimal. Remember, by the definition of minimal polynomial, if m1 is minimal, which I'm assuming here both m1 and m2 are minimal, but here I'm just focusing on this part. Because m1 is minimal, for any other polynomial, which here m2 plays the role of this other polynomial. For any other polynomial which m2 of a is 0, we know the degree of m1 should be less or equal than degree of m2. But on the other hand, degree of m2 should be also be less or equal than degree of m1, because m2 is minimal and m1 of a is 0, and by the definition of being minimal, degree of m2 should be less or equal than degree of m1. So here I have two polynomials which their degree should be equal, because degree of one of them is less or equal than the other one, and degree of the other one is less or equal than degree of this one. Therefore, the degrees are equal. So if I define the polynomial px equal to m1 x minus m2x, the point is that the degree of p definitely is strictly less than degree of m1, which is the same as degree of m2. Does anyone know why? So if I look at their, if I subtract them, the degree would be less. Yeah,
because they're monic, so the
that
leading
is
term
true.
would cancel out.
Yeah, exactly. So because m1, suppose the degree of m1 is d, it's x to the d plus other things. Remember, in the definition, we said we always assume this polynomial is monic. If it's not, you can just divide by the coefficient, right? And m2 of x has the same degree, so it's equal to xd plus other things. And if you subtract them, the factors x, the terms xd, they would cancel. So the degree would be strictly less. On the other hand, PA is equal to M1A minus M2A, but M1A is equal to 0, M2A is equal to 0, therefore this is going to be 0. So I found a polynomial with degree less than minimal polynomial such that A is a root of that. That is not possible. There shouldn't be, by the definition of M, well, we said M1 is minimal. By the definition, there shouldn't be such polynomial. Unless Px is a constant polynomial 0. So Px is just the polynomial 0, right? Anything is a root of that. And if that's the case, it means M1 is equal to M2. So we have also the uniqueness. So, oh geez. So let's look at one interesting example. It's kind of similar to a homework you had. I wanted to talk about it the previous week, but let's look at it now. So suppose M is a 3x3 real matrix such that M cubed is equal to identity, but M itself is not identity. And the question is, what are the eigenvalues of M? That is the question. Okay. What are the eigenvalues of this matrix? We have a 3x3 matrix. M cubed is equal to identity, but it's not identity. What are the eigenvalues of M?
And
So
subtract
think about
from,
it for
oh, sorry.
Yeah.
I was going to say subtract I from both sides and then substitute lambda for M.
Mm-hmm. Let's everyone think for just 1 minute. Yeah, you are going, you are on the right track.
Oh, isn't it like complex roots of unity?
You know, maybe I shouldn't solve this even this time. Maybe it's a good question for you to think about because it's not hard. Let's just leave it here. That's a good question to think about. And we don't have much time. I'd like you to think about this to see how you can use these concepts of minimal polynomial. So the way I like you to think about it is to use minimal polynomial. The reason I'm skipping that is because today I should talk, I did all these things to talk about slightly, well, also a different concept. I want to talk about something called Jordan form. So let me talk about that and compute at least one or two examples. So we say a matrix A is diagonalizable if there is an invertible matrix such that P inverse AP is a diagonal matrix. The point is that it's not true that all matrices are diagonalizable. There are matrices which you can never find such matrix P such that P inverse AP is diagonal. Are you familiar with this concept of being diagonalizable? Have you seen this before in the class? Okay,
Yeah.
great. So it's not always possible to do that, but there is a close concept. So even though it is correct that some matrices are not diagonalizable, but every matrix can get very close to being diagonal. What do I mean by that? So there is a notion called Jordan block. So suppose lambda is just a number, constant number. A Jordan block K by K Jordan block is a K by K matrix, which has lambda on its diagonal. So it is very close to being diagonal, but it's not really. So the point is that above diagonal, exactly the line above diagonal, you have one in all all entries, and everything else is 0. For example, an example can be like this: 2, 1, 0, 2. This is just 2 by 2. Right? Or 3 by 3 would be 3, 1, 0, 0, 3, 1, and then 3, and then 0, 0. Okay, that's just another example. Maybe let me write one 4 by 4 too. So let's say we have a 4 by 4 Jordan block. So let's say on diagonal we have 2. And then above diagonal, we should have 1, and everything else is 0. This is called the Jordan block. Now, this is an 4 by 4 example of Jordan block. Now, there is something called the Jordan form. The Jordan form is, so for, I would say a matrix is in Jordan form if it's built up from these Jordan blocks. So a matrix, I would say, is in Jordan form if it's built up from these Jordan blocks. Also, let me say a 1 by 1, let me go back and write it here. A 1 by 1 Jordan block would be just something like this, right? Just one number. There is no off diagonal to have 1. Great, okay. So this matrix, for example, let's say we have a matrix here. Let's say we have a Jordan block 3 by 3 here, and then a Jordan block 2 by 2 here, another Jordan block 2 by 2 here, and one, or let's say 2 1 by 1 Jordan blocks. We would say this matrix is in Jordan form. So for example, this matrix can be something like this: 2 2 2 1 1, and then everywhere else 0. and then there is a 2 by 2 Jordan block, say 3, 3. Above that should be 0. Another 2 by 2, let's say -1, -1, and then above that should be 0. And then there are two things. Let's say here we have 4, and here we have 0. And everywhere else we have 0. Anything written in that form is called a matrix in Jordan form. And then the interesting theorem is that although for any matrix A, you might not find some P such that P inverse AP is diagonal, suppose A is square matrix. That was implicit. But you can always find P such that this thing is in Jordan form. There exists P such that this is the case. Okay, let's see how we can, let me compute one example. Actually, I had one example here. Because the computations are long, it's better to, let me see. So let me write down the process, and then we would dive into the one to just look at one explicit example. So let me explain the process to you once, and then I would come back and I would explain I would answer the questions. There might be some questions here. Okay. So suppose we have a matrix A. I want to find its Jordan form. So I want to find the Jordan form of A, P inverse AP. Okay. What would I do? So again, the idea is to look for the eigenvalues and eigenvectors of A. So let's say we find all eigenvalues of A. So first step is to find eigenvalues of A. Okay, so we should do this process for each eigenvalue. So let's say there are lambda 1 up to lambda k. I should repeat this process for each eigenvalue. So I would start with lambda 1, right? I can form this matrix A minus lambda 1 times I. I would get some matrix. Now let's look for the eigenvectors corresponding to that eigenvalue. In other words, let's look at this equation. Okay, this is an equation for a vector V. V here is a vector. Okay, let's find, the second step is find all linearly independent vectors V satisfying this equation. Okay, we find a number of solutions. Let's call this the number of linearly independent things we find. Let's call that N1. This is the number of linearly independent vectors V which they satisfy this equation. N1. Okay. Now, the point is that to this number, we can assign some multiplicity to this eigenvalue. What do I mean by that? So any eigenvalue has two kinds of multiplicity. So let's keep this N1 here. So let's go to the next page. So I told you when we have the characteristic polynomial, it is of the form x minus lambda 1 to the power, say, n times some other things. And if I look at the minimal polynomial, it would be x minus lambda 1 to some other power, let's say m. Okay, and we know m is less or equal than n. This number n here is called the algebraic multiplicity of lambda 1. This is called the geometric multiplicity of lambda 1. Okay, so here we have two numbers, n and m. Each of them is the power of the factor x minus lambda 1. One is the factor in the p, one is the factor in m. Okay, so now suppose, well, look at this n. Now here I care about this n. Going back, there are two possibilities. Either n1 is less than n or n1 is equal to n. If n1 is equal to n, this process, which I'm going to explain now, is finished. We would stop here. If not, we are going to do something else. What are we going to do? Remember, we looked at this equation, a minus lambda 1I times b equal to 0. If n1 is less than the algebraic multiplicity, what we would do is that we would look at very similar equation. Not exactly this equation again, we would look at this new equation. A minus lambda 1I squared times b equal to 0. Okay, a minus lambda 1I is a matrix. I look at the square of that, multiply, I would look at that times b equals 0, and I would look at all linearly independent vectors v satisfying that. And then the number of such things is n2. Either n2 is equal to n, then I would stop. If n2 is less than n, I would continue by looking at this other equation, a minus lambda I cubed times equal to 0. And the point is that at some point, we would get to a number, the number of linearly independent vectors, and they happened to be equal to n anyway. We would stop at some point. And then I would do that for all these eigenvalues. So we have here we have different eigenvalues, lambda 1 up to lambda n, and we would do that for all of them. Okay, is there a question? Yes, that is true. The answer to the question is yes. Okay. So, okay, so suppose I've done this process. Suppose I have lambda. So suppose I have eigenvalues lambda 1 to some lambda, I don't know, k, to some number k. And for each of them, suppose I have found these linearly independent vectors v1, something like that. So there are linearly independent vectors vi I found during this process. Okay. The point is that if I make a matrix, so these are the linearly independent vectors which came out in our process, step by step. The matrix P.
Sorry, just a question. They can be eigenvectors or generalized eigenvectors?
Yes, that is true. That's why we raised it to power 2 and then to power 3 up to a moment we stopped. And we were solving all these equations, right?
Okay, thank you.
And then I would write down all these vectors from the end of process, not from, so let's say we got v1, v2, v3, etc., vt, whatever. We write down these vectors as columns of this matrix. And that would be the matrix P we are looking for. Okay, so let's see if we can do one example. The computations are sometimes quite long. Let's see if I have an example which is already done. Okay, so this process can be slightly become, okay, we have a few minutes. This process can become a little shorter with the use of characteristic polynomial. So an example. So suppose A is 1, minus 1, 0, minus 1, 4, minus 1, minus 4, 13, minus 3. Okay. Now, I want to find eigenvalues. I should form the characteristic polynomial. So I would write down the characteristic polynomial. The characteristic polynomial is lambda times, or let's say x times x minus 1 squared. I should set it to be equal to 0. One eigenvalue is 0, the other eigenvalue is 1. For the first one, the algebraic multiplicity is equal to geometric multiplicity is equal to 1, because here the power of x is 1 and it can't be less than that. For the other one, the algebraic multiplicity is 2. The geometric multiplicity, well, we should see that. It might be 2, it might be 1. Okay. Now if I form the Jordan form of this matrix, that's the point. The Jordan form of this matrix would have, it's a 3 by 3 matrix, right? It would have a part which corresponds to this eigenvalue. When the multiplicity is 1, it means the Jordan block for this eigenvalue is just one block, which is 1 by 1. So I should just write down 0 there. So whenever we have these simple eigenvalues, the eigenvalues which their multiplicity is 1, we just put them in the diagonal, and that would be it. Now and then the other numbers in that row and column are 0. Now the remaining part is related to this other thing. Okay, there are two possibilities. Either I would get a matrix of this form. The Jordan block here either is a diagonal block corresponding to eigenvalue 1, which is like this, or it would be a Jordan block, which Jordan block is like this. There is one extra 1 above. So the Jordan form is one of these two things. Either I should put 1, 0, 0, 1 there, or I should put 1, 1, 0, 1 there inside this block. And that would be my Jordan matrix. How would I understand? Okay, let me continue with the computations. How would I understand which one is the case? So the idea is that, okay, let's go to the next page. So the idea is that I have now this eigenvalue equal to 1. I should look at A minus lambda I, which is just A minus I, times V equal to 0. Now, A minus I in our example becomes this matrix: 0, minus 1, 0, minus 1, 3, minus 1, minus 4, 13, minus 4. So how many linearly independent vectors are there satisfying this equation? What is the number of linearly independent vectors V satisfying this equation? So you can answer that. How can we answer this equation? It is equal to some other quantity, we know it. Yes, yeah, that is true. So here the matrix is 3 by 3. This number, whatever it is, it's the nullity of this matrix. So this number plus rank of this matrix we have, A minus I, should be equal to 3. This is rank nullity theorem. Now, I should compute the rank of this matrix. So I guess you know how to do it. Here I would just say it. The rank of this matrix is 2. So the nullity, or the dimension of kernel of this matrix, is 1. So this is equal to 1. There is just one linearly independent vector satisfying this property. Okay. Now, the point is that if there were 2 linearly independent vectors, I would have got this one. And each of these things would correspond to eigenvalue of one of them. Now that there is just one linearly independent vectors, the other one is related to something called generalized. eigenvalue or something like that. So it should be 1, 1, 0, 1. It would be this one. And yeah, let's see if we don't have any time, right? Let's see if I can do one more example. So the class is officially over, but let me do another example to make sure, if you're interested, to make sure we can at least compute these things. So let's just, I have another done example here. Let's make it a little larger matrix. So 5, 9, 0, 0, minus 1, minus 1, 0, 0, 0, 0, 7, 12, 0, 0, minus 2, minus 3. The question is find the Jordan form of this matrix. So we should form the characteristic polynomial. The characteristic polynomial is this x minus 2 squared times x minus 3 times x minus 1. So the eigenvalues are 1, 3, and 2. This is for 1 and 3, the multiplicity, both geometric and algebraic, is equal to 1. For 2, the algebraic multiplicity is equal to 2. So if I form the Jordan block, it should be a 4 by 4 matrix, just like the original matrix. Because here the multiplicity is 1, I would have 1 by 1 block there, and that's it. Because for 3, the multiplicity is 1, I would have a 1 by 1 block there for 3, and that's it. And the rest is for 2. So there are two options. Either I would be able to diagonalize that part, which I would get 2, 2, 0, 0, or not. I would end up with a Jordan block, which would be 2, 1, 0, 2. I should understand which one is the case. So in order to understand that, I should form this matrix A minus lambda I. Here, lambda is 2, A minus 2I, and study this equation. A minus 2I is equal to this matrix, 3, 9, 0, 0, minus 1, minus 3, 0, 0, 0, 0, 5, 12, 0, 0, minus 2, minus 5. I should find the number of linearly independent vectors V satisfying this equation. As I said, that number I'm looking for, let's call that N1, plus rank of this matrix, A minus 2I, happens to be the dimension, which is 4. Okay. Now, if I do that, I would see N1 is equal to 1. So the null space is 1. There is just one linearly independent vector V satisfying this equation. So let's go to the next page. So there is just one linearly independent vector V, which means V is non-zero, such that B minus 2I V is equal to 0. Okay, so if I look at the eigenspace, so the eigenspace corresponding to the eigenvalue is equal to is one dimensional. There's just one vector, one linearly independent vector. So the eigenspace is one dimensional. The dimension of this space tells you the number of Jordan blocks. For example, if this dimension was 2, so look at the remaining part, which I should fill. The dimension we found is equal to 1. It means there is just one block which you should fit there. The point is that this one has 2 Jordan blocks. One of them is this one, the other one is this one. You can think about them as 2 1 by 1 Jordan blocks. But this one here is just one Jordan block. This dimension tells you the number of Jordan blocks you should use to fill there. If it's 1, you have to use this one. So you would end up with 2, 1, 0, 2. Okay, and the other entries are equal to 0. Okay, so that's it for Jordan blocks. I recommend you to solve some problems yourself to just figure out how you can find them. And I think the process is kind of clear. So we find the eigenvalues, we just write down the simple ones, the eigenvalues with multiplicity equal to 1. The other eigenvalues, we form that equation you saw. We find the nullity, the number of linearly independent vectors satisfying that equation. That equation tells us the number of blocks we should use, and using that we understand what should be the formation of these Jordan blocks, and we would end up having our Jordan form. Also, the order doesn't matter. I mean, if this is a Jordan form of that, also this is a Jordan form of that. I could write first 3 and then 2, 1, 0, 2, and then 1. The order and the rest 0. The order does not